So yeah, welcome again to our official start of Big Data for today. We have your homework assignment for this week is that PDF file again, and it's divided up into two parts, that true-false part at the beginning, which is really more of a check your understanding, kind of prepare for the midterm sort of part that I'm providing you the answers. So there's nothing to turn in for that first part. But then in the second part, yes, it's the final, not the midterm. The second part is a free response. I'm asking you to create a bunch of indexes that are going to help with certain queries. And so that is what is actually due for the homework this week. This PDF sort of written part is preparing you for what we're going to do next week. And next week, we'll go back into actually writing code on the computer, and we'll revisit that Twitter Postgres project with a large set of data, and you'll have to create the appropriate indexes to do various operations on that large set of data. And so in order to be able to do that, when you have, say, hundreds of millions of tweets in your data set, creating indexes is going to take a long period of time, potentially on the order of between minutes and hours. And so you'll want to really have a solid understanding of exactly being able to predict which index you'll need for which operations before just doing trial and error on that. Any questions about like either of those things to expect in the future or the homework assignment that's due this week? Okay, then today in class we'll be continuing talking about indexes and these algorithms that we use indexes for. And so let's go ahead and I'll share my screen. And so last time we were focusing on these table scanning strategies. These are again the methods that sort of the simplest select queries possible, selecting some column list from just one table, so no joins, and then where some condition. And in particular, so there's no joins and there's no group by clauses here. We saw that there were four sort of basic algorithms that we were using. The sequential scan, and this is just like a big for loop that you can always use. The index only scan, this is sort of the best case scenario for using an index, that if your table has been recently vacuumed and you're using an index only scan, then you are only going to have to touch index pages and won't have to touch table pages at all. Sometimes the table pages are called heap pages as well, so I might use those terms interchangeably. And in the documentation and any of the links references here, they'll use those terms interchangeably too. So a heap page or a table page are the same thing, and that's in contrast to an index page, which stores the actual index. And then there was the index scan. This is sort of like the base, most typical method for using an index, and the bitmap scan or the bitmap index scan. And we saw that this scan in particular is divided into two phases, first scanning on the index and then scanning on the table pages themselves. So we're going to talk a little bit more about each of these four algorithms and some more situations where they arise today at the beginning, and then we'll move on to these group by queries and these join queries. We're spending a lot of time on these table scanning methods because they really are the most important. That for any queries that you're likely to write in the future, say 90% of the work is getting these methods correct. But if you get these methods correct, the correct index scanning, table scanning technique, you'll go from a linear runtime down to a logarithmic runtime, which is enormous speed up. And what we'll see with the other methods is it's really just kind of constant factors that you're working with. So you'll get some speed up doing it correctly, but not the like huge mind-blowing speed up that we're talking about with these methods. Okay, so switched over to the terminals, and right now I have Docker running still on the Twitter Postgres project, and I'm going to start up pSQL in both windows here on the PG normalized database, and we're going to let's see, do \d tweets up above. So this gives me the relation information about this tweets relation. And again, if I scroll down to the bottom, it tells me the indexes that we've created on this table. And so these are the 3 indexes that we created last time. This, so recall that every index has a name. These are the names that I've created. The sort of customary naming pattern that I use when I'm creating indexes is you first, whatever the table the index is on, then IDX for index. It's a very common abbreviation that you'll see throughout Postgres and databases more broadly. And then some representation of the columns that I'm doing the indexing on. And over here, so we have a B tree index on country code, so CC for country code, language, lang, and then this was a multi-column index on lang and country. Let's do down here, this query select country code from tweets, just like this. And so that hit enter gives us a big list of country codes. And the key sort of technique that we're using to figure out which algorithms Postgres is using to solve these queries is this explain command. And here when we do explain, it gives us our query plan, which just explains what exactly, which of those table scanning algorithms or other algorithms that we're looking at. Here, pretty much anytime you have a select statement without a where clause associated with it, you're going to have to look at everything in the table. And so it makes sense to do a sequential scan on the table and not necessarily looking at the index. But now if I were to do modify this by saying where country code equals US like this, you can see that we have some condition over here that we're somehow making a little bit more exclusive use of our index, or filtering out which tuples we're going to be looking at. And so it makes sense to use the index for this. And in this case, we're using a bitmap index scan. Any questions about anything so far, or the setup that I have going? Okay. Let's take a look at, so one thing that we haven't talked about yet is how the limit clause interacts with our select statement. So here, when I have this this select statement like this, it's using the bitmap index scan in order to do this more efficiently. Now let's see what happens if I add a limit 10. So I don't want all of the results, I just want the top 10. And I hit enter. And you can see that now we're doing this sequential scan on tweets. This filter right here just corresponds to the condition that is in our where clause that it's filtering on as it does the sequential scan. And then this limit right here says that rather than getting everything from the sequential scan, we're just going to stop when we hit the first 10 things. In this case, so the country code equals US. Well, the vast majority of tweets are sent from the United States. And so when we're just looking at the first page file, even in our heap table or our table pages, then we're going to almost certainly encounter a bunch of tweets from the US. And so the query planner understands that, and it's going to prefer the sequential scan in this case instead of the bitmap scan. If you increase this limit, eventually we'll get it going back to a bitmap scan. So here it thinks that, okay, with doing 10,000, the sequential scan is still going to be faster, and then up to 100,000, that's when it makes more sense to do the bitmap index scan. And this is one of the really powerful things about Postgres, is that it has this very complicated and well, impressive query planner that's able to automatically determine like the constant factors of all these algorithms for us and determine which of these is going to be faster or slower based on your current hardware setup and how much RAM you have and how fast your disks are, whether they're SSDs or HDDs, and all of these things. In other database systems, so like Oracle, MySQL, SQLite, it's very common for programmers to have to specifically say that I want to use a bitmap scan on this query because the database isn't as good as at determining these things for us automatically. Okay, so this is when our country code is US. Let's take a look at the country code as China here for a second. And so with country code being China, you can see that our query plan is exactly the same so far. You can see that our estimated costs right here are different. Recall that this cost parameter is a unitless parameter, and this is just how many time units that the query planner thinks it's going to take to do these operations. And so it thinks this one's going to be about 100 times faster than this one, which makes sense because there are significantly fewer tweets sent from China than there are from the United States. We also get an estimate of how many rows will be returned. So the rows would be the total number of tweets, in this case, sent from China versus sent from the United States. Let's add a limit 10 to this one. And now you can see that there is, it's not using the sequential scan on the table. It's going to do an index-only scan on the this index right here. In this case, because there are so few tweets sent from China, it's very unlikely that in the table pages, we're going to have tweets from China in the very beginning, in the very first pages. And so that's why it's preferring to use the index in this case when our condition is CH, but when our condition was US, it's preferring not to use the index and just going straight into the table. Another really important feature about the difference between a bitmap scan and either of the other two index scans, so the difference between bitmap scan and index-only scan or index scan, is that a bitmap scan must run to completion, but an index-only scan or an index scan can return early. So what do I mean by that? With a bitmap scan, remember it's divided into two phases. That first we calculate the actual bitmap itself. This bitmap is a set of ones and zeros about which pages in the table actually on disk, which table pages we have to look at. And then once it has that bitmap, it does the heap scan, so scanning the heap pages, which is the same as the table pages, looking at the ones that the bitmap right here said we needed to look at. Because it's divided into these two discrete steps, even if I only need a single tuple, it must first completely finish this step, scanning everything in the index, and then completely finish this step. Technically, maybe we could skip this step a little bit early and stop early, but that's not actually implemented in Postgres, because when you have a limit condition, a small limit condition, a bitmap scan is never going to be chosen. With an index-only scan or an index scan, because these scans directly return either the tuple ID, the TID, in the case of the index scan, or directly return the information in the case of an index-only scan, we can stop the scan as soon as we have as many tuples as we need. And so that's why when we did a limit 10, in this case, it switched to using an index-only scan instead of a bitmap scan when we had no limit condition like this. So the key takeaway from this discussion is that if you're going to have a limit condition, you want to make sure that you're not somehow using a bitmap scan. make sure that your indexes are constructed in a way where it's possible for you to use either an index-only scan or an index scan. Are there any questions about that?
So why is it not using an index-only scan when there's no limit? Because isn't it faster?
The question is, on this query right here, it could have used an index-only scan, and why is it choosing not to do that? That is a good question, and it would be possible to use an index-only scan here. Let's see. If we do set enable bitmap scan equals off. So again, in Postgres, this is the technique that you use to enable or disable certain scanning methods. And now rerun this query plan, we can see that it's using an index-only scan. The estimated cost of this index-only scan is 0.29. Up here, the estimated cost ends up being 5. So yeah, the index-only scan definitely would be faster in this case. Well, let's see. Yeah, I'm not sure. Yeah, so I'm not sure why it's choosing to use the bitmap scan on this query up here. This is one of the disadvantages of sort of relying on the query planner to create query plans for us, is that it is possible and relatively frequent for the query planner to choose slightly suboptimal queries for us. One of the guarantees that the Postgres developers try to maintain is that you will always have an asymptotically correct query plan. So something that will give you the asymptotically correct runtime. So in this case, index-only scan and the bitmap heap scan are going to have the same asymptotics. It's just that the index-only scan would be faster from a constant factor point of view. Yeah. Let's see, possibly what could be happening is that recall that an index-only scan sometimes still has to look at the pages in order to determine whether a page is visible or not visible. And so if we do explain analyze, it'll show us how many actual pages had to be checked in order to do that. So my guess about why Postgres is choosing not to use the index-only scan here is that it sees that the I would call these pages maybe dirty pages. There are dead tuples in these pages, or we have not vacuumed them. And so Postgres thinks that the bitmap scan might be faster. Let's see if I do a vacuum on the tweets table. And now explain, analyze this, we can see that there are 0 heap fetches. And if we set enable bitmap scan to be on again and re-explain analyze, it's now sticking with the index-only scan. Okay, so yeah, what was happening here is that the index-only scan, remember, despite the name, it's not guaranteed to only look at the index. It has to look at the visibility map to determine whether a page is, or a tuple is actually visible or not visible. And that's a, if the visibility map is set that it actually has to look at the page and not just the visibility map itself. So if vacuum has not been run recently, or there's been a lot of changes to the table since the last time you vacuumed, then that's a time when the index-only scan is going to have a penalty associated with it. And something like the bitmap scan, which is already indexing the table, or looking at table pages, but doing them in the guaranteed most efficient way possible, is going to be preferred. That was a fantastic question. Any other questions so far, or any questions about the explanation of that question? Okay. So that's our discussion of the limit clause so far. Another clause that I wanted us to look at is the order by clause. So let's try the following query. Select id tweets from tweets, just like this. So it's getting all of our tweet IDs. And let's explain that query. And so we can see that it's a sequential scan. That makes sense because we have no index that uses id tweets, and we have to look at everything. So it must be a sequential scan. It's the only option even available to us. Now let's do an order by id tweets, like this. And here's what the resulting query plan looks like, that it still has this sequential scan, exactly the same as it had before, but then it has this sort key right here. And this sort key is because the table, recall the pages inside of the heat pages, the table pages, there's no fundamental ordering to them. They're just whatever Postgres happened to put them in. And so we still have to sort them afterwards, and that's what this sort step says. Whenever we use an index, however, indexes, the B-tree index in particular, maintains all of the entries in a sorted order. That's the way it's able to sort of do its efficient search. And so the B-tree index is able to take away these sort steps for us. So sorting is a relatively expensive operation in login, and we can get that away with a B-tree index. Another thing about this sort step is that if we wanted to combine order by with a limit clause like this, we still need to have a sort step inside of here. And so it's doing our sequential scan. In this case, it's decided to parallelize it, doing the sort here, and then at the end, doing the limit. The sort is still going to be a full sort over the entire results returned by the sequential scan right here. So it's still going to be a relatively expensive operation. This limit by is not gaining us any speed up. We still have to compute the full query. So let's create a table, or let's create an index. Create index tweets idx underscore id, like this, on tweets id, oops, id tweets. There we go, create index. And now if we rerun this explain, we can see that we're doing an index only scan. So that's great, super fast. There's no sort step anywhere, and we still have our limit right here. If we were doing, say, instead of selecting id tweets, let's select id tweets, comma, lang from tweets, order by id tweets. Now we no longer can do an index only scan because there's no index that contains both id tweets and lang. So we fall back to an index scan, and the index scan still returns things in sorted order, and it still returns things sort of one at a time rather than as a big batch at the end. So we can go straight from our index scan to this limit and getting the full speed up. The takeaway from this is that whenever you really need to have something that your results being ordered by, you want to make sure that you have a corresponding B-tree index in order to do that ordering by. And that B-tree index is going to, assuming you're doing an index scan or an index only scan, you'll be able to combine it with that limit to get fast results that way.
My quick question,
yeah.
Might be a little off topic, but how do we interpret the notation of these costs? I understand the first little bit, you know, point set for a limit would be 0.042, but what's with the 2 dots 2.41 going on after
good
that?
Question. Let's see. My memory, which might be off, is that the first one is the setup cost. So in order to set up the fact that we're going to do an index only scan, it takes this amount of time, and then this is the predicted time to actually perform the scan. certain operations take up a lot of setup time, but then very little actual runtime, and things like an index-only scan are sort of the opposite of that. When I am interpreting these things, I generally, yeah, I guess actually I don't even really look at the cost numbers very much when I'm figuring things out. I'm only really looking at the actual algorithms, and then assuming that my sort of internal sense of which algorithm should be best for this situation is kind of correct. If I was really caring about these numbers, then instead of explain, I would be doing explain, analyze, and the numbers over here in the same format. And yeah, I'd have to look it up in the docs to be sure, but I'm pretty sure it's the setup cost and then the actual runtime cost. One of the maybe useful things to be on the alert for is when you're doing an explain analyze and the costs, the estimated costs and the actual costs are very different from each other. That is like a potential red flag of you should be paying attention to what's going on here. In this case, the reason this estimated cost and the actual cost are so different from each other is because the estimated number of rows and the actual number of rows are so different from each other. The estimated number of rows in this case is different because we have this limit at the end, and the index scan, when it's deciding to use the index scan, it doesn't actually know yet that there's going to be a limit taking place at the end of it. So it doesn't know that there's only going to be 10 rows extracted, and so that's why this estimate right here is so high and this estimate here is so high. Yeah, it's a good question. When, yeah, what we'll see is for your next homework assignment, things will be written like explain costs off, where it doesn't actually give these numbers over here, because these numbers are, so they're very ephemeral. They depend on lots of conditions inside your system. So like how much free memory you have, free disk space, whether there's other processes currently running or not currently running. And so when you were to run this command, or if I were to run this command multiple times, I might get different numbers here. And in order for like the test cases to work, we'll just have it done with costs off like this. And I think the vast majority of people, even though it defaults to the costs being on, sort of just think in terms of the costs being off and look at this information right here as their actual debugging information. Great question. Any other questions so far? Okay. Let's see. So the next thing I want to look at is this following query. Select id tweets. Oh, I guess we started this, but we didn't finish it. From country code, oops, from tweets where country code equals US like this. And let's add the explain spelled correctly out front like this. And we're getting our bitmap index scan on index country code. The reason why we have to use this index right here is because the id tweets right here is not part of, if we have these indexes up here, the only two indexes involving country code are these. There's nothing involving both country code and id tweets. So let's modify this now so that we have select lang. And so now we can use an index-only scan from this index right here. And we talked, let's see, let's also do now, yeah, let's start with where lang equals English. Here is an index-only scan on this index right here. And let's think about why is it choosing to use this index instead of this index. For this particular query right here, it would be possible to use an index-only scan on either of these two indexes because they both contain all of the information needed for the query. In order to help demonstrate that, I'm going to temporarily delete this index down here. So inside of Postgres, this is one of the other unique features about Postgres that's not part of other databases. You can do all of these what are called data definition commands, so like creating indexes, creating tables, these sorts of commands inside of a transaction. And again, other databases, you can only do like inserts, updates, selects inside of transaction, but you can't actually modify tables or indexes inside of a transaction. So what I'm going to do is I'm going to drop this index right here. Oh, sorry, drop this index right here, delete this index. This is the index that we were previously using. So drop index like that. And now rerun this command right here. And we'll see now that it can't use this index right here because it doesn't exist anymore. It's going to choose to use this index right here. The estimated costs you can see are a little bit higher when using this index. If we were to, I guess we can't go back and do the explain analyze on this one anymore, but we would see that the run times are also a little bit higher using this second index. And so why is that the case? This is an important and very subtle concept. And the reason why this is the case is because the fan out of the B tree is different in this index and this index. Fan out of the B tree is different in these two indexes. Recall that the fan out of the B tree, each node of the B tree is going to store as many elements as will fit in a single page in the index. Each element is a tuple corresponding to all of the entries that we are indexing. So in this case, the tuple that's in the B tree index page only contains the lang field. In this case, it has to contain both the lang and the country code field. Because it contains more information, it means fewer tuples can fit inside of the page. So because this index contains more information, the tuples are larger and fewer fit in a page. This means that the fan out is going to be larger, or sorry, the fan out will be smaller. So the height of the tree is larger. In this particular case, we're still working with a relatively small data set of only 150,000 tweets is what I have loaded. And so the height of the tree is probably just 2 for both of these cases. But once you were getting to like terabytes of data, loading up the entire Twitter data set, if you have a fan out of 500 on a, say, 10 billion entry table, that's only a depth of 3. But if you have a fan out of 2 on a 10 billion entry table, that's a depth of 30. And so that's a significantly larger fraction of pages that need to be accessed. The asymptotically, you still get the same performance, still significantly better than doing a sequential scan. So this is not a bad index for this query by any means, but this index is the better index. Are there any questions about why this index would be preferred over this index for these queries right here? Okay. Let's take a look now about what happens if we do country code. Country code equals US. So here, the index only scan is on this index. That's great. That index still exists. We haven't dropped it. And so we can use it. But now let's drop that index. And run this command right here. And I'm going to change our country code to China. Oh. Okay, it still wants to do an index-only scan. Let's think about why, or what the potential disadvantages of this index-only scan are. It's doing an index-only scan on the second column instead of the first column. So whenever each of these tuples is stored inside of the index, let's go ahead and switch over here and actually draw this out. Each one of these tuples is stored in the index. It's being stored as the first lang, and then write CC for country code. And whenever we're doing a less than or greater than comparison, it's always going to first do it on the language and then do it on the country code. So if we had, say, English US like this, and English China, and then Spanish, ES is Spanish, then US. When we're searching on the country code field, we want this entry and this entry to be next to each other in the index because they have the same country code. But in the B tree, it's going to put this index and this index next to each other rather than this index and this index next to each other. Because of that, this index right here is a relatively poor index for this, this query. It happens to be the case that the country code and the languages that a tweet are sent from are very highly correlated with each other. And so in order to find the country code, let's see, in order to find the country code with country being CH, country being China, mostly those will all be contained near where the language equals Chinese area are. And so it can still use the index a little bit, but it's not nearly as efficient as if the index was a country code comma lang index. So if I do create index CC lang on tweets country code comma lang like this, that index will be much more preferred than this index up here. If you're looking at the estimated runtimes here, you can see the estimated runtime for this 6.5, whereas the estimated runtime for this up here 1600. So the order for a B-tree index, the order that you put these keys in is crucial, and you always want the sort of keys that you're doing comparisons on most frequently to be towards the left of the index, or towards the left of the column list. Any questions about that? Okay. Few more syntactic things when we're creating, let's see. So I'm inside of a transaction right now. So I've been creating and dropping indexes. So let's just verify that those transaction effects are taking place. So down here, we have different indexes visible down here than we have visible up here. Just rerun that command up top. And you can actually see that because we've been doing those operations down here, it's not even going to let me finish this command until we either commit or abort this transaction. Let's go ahead and abort it. As soon as we abort it, this command up here finishes, and now we have these indexes right here that are available to us. The next thing that I wanted to show was, so here with this right now, it's going to use the tweets, IDX, CC, this here, this query selecting country code where country code is equal to something in particular is going to use the country code query. Let's go back to select the, we'll do select the country code where the language is equal to English. And it's going to use the lang CC, being able to do an index only scan on this right here. It's very common, however, to maybe we're really, really interested in the situation where the language is equal to English, and we care a little bit less about the other languages. And so I might want to create an index specifically for the condition where lang equals English, not just conditions on the lang in general. In order to do that, it's called a partial index. Create index tweets IDX, and we'll do CC lang English on tweets, and I want country code, and now where lang equals English, like that. So we already had an index that looked like this, but now I'm adding this where clause to the index over here. What this where clause means is that the index will only contain tuples that already satisfy this condition. And so now when I do this, it can really quickly do an index only scan on this new index that I've created. This new index is going to be a really, really fast index. It's going to be much smaller in size than our other indexes because it has this condition on it right here. It's also going to, let's see, so because it's smaller in size, it'll be much faster to update when we're adding new tweets into our tables. We don't have to update this index unless this condition is satisfied. All of the other indexes that we have, they're giving us overhead on our inserts because we have to maintain all of those indexes every time we do an insert, update, delete. It's also going to be faster because of those fan out issues that previously we were using the lang CC index, this index right here that has multiple columns inside of it. Multiple columns reduces our fan out, increases the depth of our index. By using the partial index, I can still use the fact that we're able to, that we have this extra information here inside of our select query, but I no longer have to store 2 columns in the index. I can only store 1 column. So the fan out is much higher, the depth is much shorter. I'm going to access fewer pages when I do my index scans. Any questions about the partial index or the advantages, disadvantages?
How is the fan out higher? Because isn't it the same data type that we're storing?
This is a good question. So this index right here compared to this, oops. Yeah, so this index right here, CC lang in compared to this index right here, the fan out is the same. Adding the partial constraint right here doesn't change the fan out of this index. But previously I was not able to use this index for this query right here. Instead I used this index in order to do an index only scan. This index, the lang CC index, contains both the language and the country code inside of it. And so it was possible to do an index only scan on this because we were selecting the country code and the language. The partial index allows us to continue using an index only scan with fewer columns. So because we're using a partial index, the fan out of this index is less than the fan out of this index, and we're still able to use an index only scan. The fan out of this index is the same as the fan out of this index, but this index is not able to do an index only scan. It's a great question. Any other questions about that? Okay. So what would happen? Let's think about what would happen if, so here is our explain query again. What if instead of where language equals English, I want where the lowercase version of language equals English. And now we can see here that the query is not able to use our partial index like this. In general, anytime you're using functions inside of a select statement, somehow modifying a column that's either one of your where conditions or, yeah, really that's one of your where conditions, the Postgres is not able to map, it's not able to understand that in this case, lower is actually going to be idempotent. It's not going to change this value at all. And so we could still have used this same query plan from before. It's going to give us the exact same results. Postgres doesn't know that. So if you wanted to be able to use functions inside of your where conditions, inside of your partial indexes, you have to use the functions like this. Oops, that's not the, there's the create partial index. When you're creating it, you have to put the functions on your conditions like this. Or if your condition is going to be on an actual column inside of the table, then you have to put the functions inside of here. You can have arbitrary functions on columns inside of your column list right here, and you can have arbitrary functions on columns inside of your where conditions over here. Okay, a few more concepts related to table scans and indexes, and then we'll be done with this section. The next concept is what's called a unique index. And in a unique index, this is how Postgres implements unique constraints. So right now we have this index on our ID tweets. I'm going to go ahead and drop that index. Whoops, drop index tweets IDX ID. Probably should have done that in a transaction just to be safe about doing things, but I was pretty confident that was the right command to do. And now let's do recreate that same index. Create index tweets IDX ID on tweets tweets like that. So that just dropped it and then recreated the index like this. This index right here is not enforcing that the ID of all the tweets will be unique. There's currently no constraint on the really there's no constraints in this table at all. But there's nothing enforcing that these tweets be unique. And if I wanted to enforce that they be unique, it's create unique index like this. Now up here, I'll press Q, relook at this, and we can see right here, we have this unique index created right here. Indexes are important for unique constraints because if we have a unique constraint, every time you do an insert or an update, you must look through the table somehow to make sure that that value doesn't already exist. And the index is going to make us do that in log time instead of linear time. And so that's why the syntax is sort of built into the indexes, that you must have a index in order to do a unique constraint. Most of the unique constraints, though, that databases have inside of them are not created directly with this syntax. We've seen before that the primary key syntax creates the primary key is equivalent to unique and not null. And so whenever you're in your table schema, see primary key, that's automatically creating a unique index for you under the hood. Foreign keys also create indexes for you automatically. It's potentially confusing about which indexes a foreign key does or does not create, because there are multiple tables, multiple columns that are being referenced with that. And rather than telling you exactly which indexes that is, that's one of the things for your homework assignment this week I'm asking you to look up. And you'll need to know that information both for the true and false and for the free response portions of the homework. So it's important to look up which indexes do foreign keys create. All of the other constraints that a table can have, whether they are like the not null constraint, or if you're checking that integers must be positive, some sort of constraint like that, those constraints do not require any indexes. The only constraints that create indexes are the unique constraint and the foreign key constraint. Let's see, that finishes our discussion on the things that you need to know for indexes and table scans. Are there any questions about any of that? Okay, so all the things that we've talked about so far, I'd say are like the most important things to understand when it comes to optimizing your queries in Postgres, or really any database system. But the actual examples of queries that we've seen before are relatively boring queries, relatively unsophisticated. And so now what we're going to do is create more interesting queries and see how Postgres is going to answer those queries, and how those answers will relate to the things that we've seen so far. So as a first example, let's do, actually, before doing that, there's one last concept that I did want to cover in about the previous material. So sorry about that. Let's do a select id tweets from tweets let's see. I'm forgetting exactly which command we used that got us our bitmap scan before. It was select, here we go, lang, comma, select lang from tweets where lang equals US, like that. Whoop. Lang equals English, like that. There we go. And explain that. That's a index only scan. I think because I vacuumed, we might be only in index only scan territory now. Let's add. There we go. There's our bitmap index scan. So here, this is a bitmap index scan because id tweets and the language, they don't have any indexes that share both language and id tweets as either columns or constraints on the index. And what I want to do is I want to look at how many pages in the table file actually get accessed by this command right here. So when I use the analyze command, you notice that it added this heap blocks right here. And this heap blocks is actually so in Postgres, a block is a synonym for a page. So this is the total number of pages that the bitmap index scan right here says that we need to check inside of the tweets table when we do a heap scan. So this is something that it's not reported in the explain query plan by itself, because we don't actually know what that number is until we execute the query. And recall that explain analyze actually executes the query and reports back some statistics on the execution. So here it's accessed about 7,500 tuple pages. This particular data set, so it's real quick, select count star from tweets, about 150,000 tweets. And if we look up here, you can see that there's quite a bit of information stored in each tuple. And I haven't done anything to optimize like the column Tetris. So it ends up being about 500 bytes or so per tuple. So it can store about maybe 16 tuples per page. And so there's about 10,000 or so pages. So this is accessing about 75% of the pages. That's a pretty inefficient use of our index, that we're still almost doing a complete table scan here because the number of tuples or number of pages that we have to access is so large. When this is the situation, it's there's one thing that you can do to fix this, and that is you can reorder the tuples inside of the table pages. This is called clustering the table according to an index. And the command is cluster, then the name of the table, in this case, tweets, and then using whatever the name of the index is that we want to cluster on. Since this is the index that's being scanned, I'll use this index right here. And I guess this is a partial index, so we can't use that. Use the there we go. An index that actually exists and is not a partial index. You can see that the cluster command took a little bit longer to run than our create index commands. Clustering is an expensive operation. You should think of it as similar to the vacuum full operation. It actually rewrites the entire table on disk. And it reorders those tuples so that they are ordered how they're ordered inside of whatever index you have right here. Now, when I do this explain analyze, you can see that the heap blocks has been reduced from 75,000 down to 52,000. And so the actual query itself has been, the runtime's been reduced as well. It was 59 milliseconds here. What was it up here? In this case, the execution time went up probably due to random load factors on the machine. But in general, the execution time will go down because the number of pages actually accessed will go down. We can recluster this on a different index. So IDX ID, the ID, the tweets ID is totally uncorrelated with the country codes or the language. And so now if I re-explain our heap blocks goes up again. Clustering is just a one-time operation that as soon as you are done clustering and then inserting and deleting more tuples from the table, Postgres makes no effort that those inserts and deletes and updates respect the fact that things are clustered. So there's a good thing to do if your database is like a one-time load up a bunch of information to the database, and then you're going to be doing a bunch of select statements on it, but no inserts, updates, deletes. If you're going to be doing a bunch of inserts, updates, and deletes, clustering is not going to help you at all. Any questions about the cluster command? Okay. Then now we're ready to talk about these more interesting queries. So we'll do select lang count star. We'll start by talking about aggregates from tweets, group by lang, like this. So this is actually the first moderately interesting query that we've seen so far, counting all of the number of times, number of tweets that we have for each of these languages over here. And if we explain this, you'll see that we get a fairly complicated looking query plan out here. Let's do add a where lang equals English, like that. And we get this simpler query plan here. Up above, where we had no conditions on our table, we still had to scan the entire table. So that's where this seq scan is coming from. It's doing it in parallel. So the parallel is adding a little bit more complexity to this. But the fundamental thing is that seq scan here. We'll also see if we scroll up a little bit, there is this group aggregate and group key. These are the operations that actually do the handle the group by clause and these aggregate functions. And you can see that down here, group aggregate and group key lang, these look exactly the same as these down here. The difference is just that because I added this condition right here where lang equals English, we were able to use this, in this case, bitmap index scan, in order to get rid of a sorting operation and the seq scan right here. So what we're going to talk about next is exactly what this group aggregate is and how it's implemented. Inside of Postgres, there are two aggregate methods, group aggregate and hash aggregate. Let's scroll down. Here they are, the aggregate strategies, hash aggregate and group aggregate. What we'll see is that the sort of runtime performance of both of these is really, really similar, and so you shouldn't have to think too much about these operations. But there's some good slides right here that I'll go over, which explains how these operations work. So this is the link to these slides. This is a presentation that this person gave about query optimization in Postgres. So one of the goals of our discussion for like this kind of whole section of the class is that this is the sort of presentation that somebody could give and you would be able to understand what's going on. We're really only scratching the surface about like all of these query optimization details and what you can do to optimize your queries. And these sorts of presentations are sort of both the next step and the last step, the only real thing that you can do to get a deeper understanding of how to optimize things. There are no like textbooks or anything like that that talk about this. The sort of active area of ongoing research. So in this presentation, start off with what is grouping. So here on the left-hand side, if we had this sort of table information where there's the equivalent of two columns, a numbers column and a color column, and we're grouping by the color and then summing the numbers. So first, this is grouping by the colors and then summing all the reds to get 15, summing all the blues or greens to get 8, summing all the blues to get 9. And how can we actually computationally do this efficiently? In SQL, here are the sorts of queries that we're looking at. So anytime you have an aggregate function like average, min, max, these sorts of functions, and then group bys. Anytime you have an aggregate function, recall that all of the other columns need to be in your group by clause down here. This is maybe a little bit less obvious, but anytime you have a select distinct, that's also doing an aggregate. If we were to select colors distinct from this, then the aggregate would be like throwing away everything outside of these colors. So select distinct also follows these algorithms. Postgres allows the syntax of select distinct on, so there's only one column that has to be distinct. That's also using these algorithms. When you have a aggregate function like max, but no group by, it's still using these techniques. And here, This order by and limit, there are multiple ways that Postgres can implement this. One of them is by using these techniques here, but also using the index and the limit techniques that we saw before as a different alternative Postgres can choose. Okay, so how does it work? Inside of, if we have one of these queries like this, so here we're thinking about the sum, how we actually compute the sum on this column, where we have the values 2, 3, and 7 in our table that we're summing over. Then what's happening is that each one of these functions, each one of these aggregate functions has an internal state and an internal function about how it maps state given the next value onto its new state. So for sum, the initial state is 0. Our value up here is 2 in this white box. And what sum does is it just adds 0 to 2, giving us 2. So now on the next row, each one of these big circles represents what we do on a row. Each one of these square boxes in yellow represents a row. Our next row contains 3. The way we aggregate it, 3 plus 2 giving us 5. And then 7 plus 5 giving us 12. The result is 12. So it's just this diagram is sort of a complicated way of saying what you would intuitively expect sum would be doing. The average is a little bit more complicated because there are two things that we need to take into account for the average, the total number of things that we've seen so far and the sum of those things. And so now there's our internal formula is a little bit more complicated. When we get a new row 2, add 1 to the count equals 1 now, still summing the input. So count equals 1, count equals 2, count equals 3. And then the sum is the same as it was before. Sum equals 2, sum equals 5, sum equals 12. And then we take these internal states and actually apply our average formula to get the final result. So this is internally just what's going on. The important thing to know is that it just happens one step at a time, that it takes in one input data point at a time, computing some intermediate step. There's lots of different ways that you can implement these. We will talk later in this class about how you can actually create these functions, but that's not important for us now. What's important for us now is that there are two sort of techniques for actually implementing this, the group aggregate and the hash aggregate. When we were looking at our query plan before, we were using a group aggregate, and we know that because it says group aggregate right here. For the hash aggregate, it would say hash aggregate right there. And so this diagram is going to explain what the group aggregate does. You'll first notice that the input over here, this left hand, the stuff to the left of the 0, this is all of the information in our table, all of the rows that we're going to be considering. These rows are already sorted according to the colors, according to the thing that we're grouping by. And that is required for the group aggregate. You have to previously sort according to the thing that you're grouping by. Up here, when we had no index, we did a sequential scan. You'll see that next it did a sort right here on the thing that we are grouping by right here. And it needed to do that sort so that it could do a group aggregate up here. If you have a group aggregate, there must be sorted data. This sort we were able to skip though down here because when we do a bitmap index scan, any index scan, whether it's a bitmap scan, index only scan, is guaranteed with a B tree to give us sorted data as a result, so we can skip that sort step down here. It's another one of those benefits of having the index. And the group aggregate, one of the key things to know about it is it requires sorted data. Back over here, how it will work is it will step through. So in this case, these two rows, the 1 and the 2, have both been processed. The state over here is equal to 3. Now the next 3 rows, this 3, this 1, and this 3 are all being processed. We're totally done with the blue. So this 3 plus this 3 gives us a 6. We've outputted the 6 and we're done with it. We'll never consider the blue column again. If we were to have a limit 1 on the output of this result, then we could instantly stop here and we wouldn't need to continue processing because we've outputted some results. But if we don't have a limit, then we continue processing, process the green one state using that same step-by-step procedure. And so we process this 2 and this 2, So that's 4 plus 4 gives us 8. Here's the 8, output that 8. If we had a limit 2, we could be done, but no limit, we keep going. And so now we have to process the red ones. And so just for space reasons, this has all been combined into just 4 steps, but in reality, it's just going 1 row at a time, 1 row at a time. And you get this output like here. The hash aggregate works differently. In the hash aggregate, you do not have sorted data like this, no sorted data as input. And instead, in the intermediate step over here, the square box, it's just going to compute the states for each one of our colors, each one of the things that we're grouping by. And because the things are not sorted, so here we got the 3, now there's 2 internal states right here, 2 internal states. Because the things are not sorted, we don't know whether we're done with the blue one when we start the green one. And so we can't actually output things yet. We must continue going. And we must continue going. At this point, we've done a lot more processing. We are in fact done with the blue one, but we don't know it yet because we haven't looked at any of these over here. So we still can't output the blue one. We have to keep processing. And only once we've finally computed everything can we actually output anything. So that's sort of the big picture advantage of the hash aggregate is that you don't need to have sorted inputs, but the big picture disadvantage is that you can't output things one at a time. You have to output them all as a big group all at once. And so after this, it outputs it. This table right here summarizes all of the things that we just said and the advantages and disadvantages. And for the true and false question on section on the homework, this is the main reference that that you should look at. Let's see, we don't have enough time today to talk about the join algorithms. That's okay. We'll talk about those on Monday next week. So because of that, I'll make the homework. You can have a week extension on the homework. So it won't be officially due until next Sunday. We've covered everything that you need for the homework except for like 2 questions on the second section. So I do recommend getting started on the homework. You can do the vast majority of it at this point, but we'll cover those joining algorithms on Monday. Yeah, so that'll be the end for today. We'll have I'll be available on Friday for the lab. There's no particular lab work, but that'll be a good chance to ask questions about the homework and why certain answers are the way they are. I'll stick around to answer any questions that people have about anything, but otherwise I will, that's it for today, and I'll see you either on Friday or next week.